is that we have these wires, and Peter, who's somewhere maybe here, he will talk about them in detail later. These are indium arsenide wires with aluminum that we heard, aluminum shell that we heard about earlier. And we think we can bring them into the topological regime. At least, they show all these nice features that we associate to Majoranas. This particular one, which was published last year, is with a dot in the end. So it's a design with a wire and a dot, and it's actually an accidental dot. It wasn't produced to be there. But nevertheless, if one changes the gate voltage here, one sees clearly dot behavior. These Coulomb peaks, source drain gate voltage plots. So this is a zero field or low field. So if we put ourselves here in the middle and look what happens in the middle as B is increased, there's this a number of subgap states inside here which we associate to the wire then. In particular, there's one which seems to pin at zero energy, and true enough, as a function of B field, these are the subgap states that go in and then pin in the way we've seen before. And I would like to think of this as the Majorana state. And here are cuts in the IDV as a function of voltage. One could be concerned about the size of this peak. This is something we're thinking about. It should be 2 e squared over h. It's not. And my personal belief is that it has to do with, also other people here, I think, has to do with disorder. And a P wave is really hard to get a clean, strong gap because disorder actually produces in-gap states. So that's something that needs to be sorted out, either by, we figure out why this is, or even better, make better materials where this problem is not there. Because then we don't have to think about it. Peter. All right, so this is the device we would like to think about now, because it has this dot that I said, which is unintentionally there. And we can follow the different states, either a dot state or wire state as a function of the different gates, G1 or G2. So G2 mostly couples to the wire, G1 mostly to the dot. And there seems to be two kinds of states, one which is a wire state, one is a dot state. So if we put ourselves in a sort of or follow the dot state, go actually across it, which is this yellow spot here, then we see that the cross is zero because we are going through a resonance of the dot. All right, so this was a zero field, crank up field. Now subgap states are coming in, pressing this crossing down to zero. And after this transition where we have the Majorana, another state appears at zero energy. And this seems to make an anti-crossing now with the dot state. So this is what we would like to think of as dot state, and this is the Majorana, and they make an anti-crossing here. So we have been simulating this setup, and I will show later what goes into the simulation. So this is before the transition, the topological transition, and this is after, where first we have a cross, and then after we have this anti-cross with the Majorana going through. And you see it looks very much the same. Even the colors are the same. So so if you want to have a way to think about what happens when we tune this dot, there's a small simulation here. So this is the wave function in the wire. In the simple model, there's a Majorana peak here, Majorana peak. They now overlap, so that's why they're also something in the middle. And then there's a dot state, which we now tune, changing the potential there. So it's running now, you see. Once they come into resonance, this Majorana leaks out into the dot, which changes the overlap between the Majoranas and make them split. But before they were not split, even though they looked like this, it looks like they have an overlap, and surely enough they do, but the splitting is for some reason zero. So you can put yourself, if you go back in B field, you can put yourself at a point where it's not split and do this experiment. You can also try to put yourself on a point where it is split a little bit, and sometimes they do this moving in and out, so you can put yourself there. And in this case, it would do the opposite, that it's split here, and then you go into resonance, and you can make it less split. So reason is that you simply change the wave function in Majorana due to this leaking out in the dot. So that, that physics seems to be okay, at least it makes sense. So these wires, they have nice zero bias peaks like this one, which are just astonishingly flat. Most theory plots would make an oscillating behavior here, but so there are still things we don't understand, but this is a particularly nice one. So what goes into the modeling? So we study this the inverse Green's function of the wire. So we have a model of the wire Hamiltonian, which has kinetic energy, spin orbit, Zeeman energy, and then the self-energy due to tunneling to the superconductor. You integrate out the superconductor, you get this self-energy term. So this inverse Green's function then goes into an S matrix, which goes into calculating the conductance plots I showed you. But we can also just look at the poles of this inverse Green's function, or the Green's function, and to see, to understand this level structure, and try to extract some parameters from the experiment. And if one solves this equation, you see there will be an induced gap, which we call induced at zero voltage, or zero B field, sorry, which is this value here. And delta is the bulk, BCS. And then one can, from this, extract this coupling parameter that goes into the self-energy, and it turns out it's in the strong coupling regime. So this gamma is stronger than the bare delta in the bulk. One can also try to get the level spacing, looking at how these anti-crossings are. And with some hope or some success, try to estimate the spin orbit parameter. And there's an important thing here, which is the renormalization factor that comes from solving this equation. S matrix term? This one? Well, there's an assumption of, you say that you have the wire which couples to the superconductor, and it's only local. So you integrate out the superconductor, you go in, second order, come back, and you keep only local one because you have very different Fermi vectors in the wire and in the superconductor. So yeah, so in a point, which I think is a good approximation. There also, in particular, this paper does a similar analysis of like this one here. Okay, so we can try to extract parameters, and it turns out that we are in the strong spin orbit regime, actually. So the spin orbit energy is of order the gap. Other design possibilities is to use 2D designs. This is a recent paper I didn't put on the reference, so it's on the archive. It's also from our group. I only show Copenhagen data, of course, because being a nationalistic person. It's so fashionable. So this is now a 2D. I think Peter will talk about this. Will you not? No. Okay. So it's a two-dimensional indium gallium arsenide, indium arsenide, indium gallium arsenide structure, and then this potentially grown aluminum, which can then be removed, and gates. So now we have a possibility of actually making the patterned structures starting from a 2D system, which, if this will turn out nicely, it will be really a powerful platform, I think. But let's see in the future. Okay, so that was what we can call spectroscopy, where we tunnel into a Majorana on one end, have it well connected to a drain at the other end. There's also this experiment that Jan showed earlier and explained nicely, where you see a transition from 2E, where transport is through Cooper pair tunneling, or two-electron tunneling, and to a transition with single-electron tunneling, which is because of this subgap states that eventually creeps down to zero. And as Jan also said, this is what you would also see in a normal state, but this is clearly not the normal state, because the normal state happens out earlier. We can see what field it takes to kill the superconductivity. And once that happens, it really doesn't look like that. Then it's just flat and doesn't have all this structure. So it is some kind of subgap state that seems to be at zero energy, and so it does some of the right things in sense of going down exponentially as a function of length, even though you're not supposed to be in the exponential regime for such a short wire maybe, but nevertheless it goes down. Recently there was another experiment with the same type of device, might even be the same device actually, with a different gate voltage. Well, again we see this transition from 2E to 1E, but in addition there are what we call ghost features here. So this is 2E periodic, and then for some reason it's also this additional feature which makes it look like 1E. And the way we interpret that is that this has some non-equilibrium state that's occupied, because these are these parabolas that you saw earlier this morning, and this is these two states here are these 2 points, and this is 2E. But if you happen to occupy yourself up here in a quasiparticle above the gap, you kicked up into a odd state, and now you can run current through these states, and then you can fall down and you're back to having no current in here. So it gives a way to look at the dynamics of quasiparticles jumping in and out. So this is a result of a simple rate equation where we include just not the lowest parabolas but also the upper parabolas, having some rate for generating quasiparticles either from the lead or internally. Actually you cannot see the difference between the two. And of course some assumption about how fast it relaxes. And that will produce that produces this kind of theory plot for the diamonds source drain gate voltage plots, which has a lot of resemblance to the experiment. Again, the colors are the same. So you see all this NDR, you see the main peaks, the 2E main peaks, and then these ghost peaks inside here. So the contrast of how strong these 2E or these ghost peaks are, of course, depends on all the parameters. And with some assumptions, for example, there's one assumption about relaxation from a above gap state to the sub gap state, which we had from an earlier experiment, say 0.1 microsecond. Then you can try to see which quasiparticle generation fits the experiment best. Okay, so let's say this 1 microsecond seems to be okay. So this is in some sense a poisoning time. At least this is the poisoning time in the simulation. It doesn't necessarily mean this will be the poisoning times once we use these for qubits, because that's a different kind of process maybe, and it's a different kind of relaxation, and yeah, so don't take this as a number for this will for sure be the poisoning time in our quantum devices later, or we can hope. All right. So with these elements, we can try to say, with the present technology, what can we hope to make of qubits based on Majorana and their wonderful properties? Well, first of all, it should be 1D structures with semiconductor covered with a superconductor, and they should be parallel so that we can put a homogeneous magnetic field and then make this topological and this topological at the same time. So these T-junctions that people liked, at least for the moment, they're not so easy to make. We can also fairly easy make quantum dots and build into this structure, because it's just the same wire which is covered by superconductor here can be used to make a quantum dot if we apply some gates here or put some gates. And then we can have coupling, controllable coupling between a dot and this Majorana wire. One more thing we will need, which doesn't work yet, is to have a superconducting bridge that connects these two wires so that we can have this box that Aaron talked about earlier today, so that this will be one combined Coulomb island with a common Coulomb brigade, charging energy. So it seems like a trivial thing because this could be any kind of superconductor, it doesn't have to be topological. But okay, so there's some material issues. This hasn't been made yet, but hopefully it can be made. And then also we would like to have another bridge, which in this case is a semiconducting bridge, to make interference loops. When later we'll show you how we think one can manipulate this box by tunneling electrons either through the box or through the bridge. That will be sort of the workhorse of the proposed qubit. So this is what we have to play with for the moment. And the dimensions are such that, well, this should be shorter than the coherence length of the semiconducting bridge, and this should be longer than the coherence length, or the superconducting coherence length. This is the dephasing length of the topological superconductor. So they're long and they look like that. All right, so this will be the qubit we will suggest. It's made out of 2 wires with 4 Majoranas, and the Coulomb brigade then acts to fix the parity of each island. So in terms of Majorana, the product of all these Majoranas is 1 or -1. And it's a qubit, and because it's a 2-level system, originally we had 2 times 2, but then Coulomb brigade brings it down to 2. With for example, a choice would be to say that this times this is the Pauli x, this times this is the Pauli z, and this times this is the Pauli y. So that's the qubit. So how can we address it? We can tunnel electrons in and out, either from a dot, which we'll have later here, or a lead, or we can couple electrically to it, and so the Hamiltonian to describe this is this one. We have charging, and we have tunneling in and out of the box. And then there's the Hamiltonian of the Majorana system, which is in the simple case just 0, so that's an easy part. And then there's a Hamiltonian of the dot or the lead. So second order perturbation theory, which we saw already this morning also, you go in, you go out, gives you a effective low energy model here where gamma I, gamma j addresses these two, so that's like a Pauli operator, and then takes an electron from here and puts it there with something that has to do with tunneling in or tunneling out intermediate states, the energy of that. So the phase of this tunneling going through here is, can change sign depending on the state of this Majorana pair. All right, so yeah. I mean a quantized dot. Yeah, it's leaking. This is the second order perturbation theory. That is the leaking. Yeah. No, it's not, because that would then you would have to say you have to go to some order in tunneling, and it doesn't jump out because of charging. Okay, so it will leak out. You can say you tunnel in, you tunnel back. That's a second order process that that conserves the total charge on the island. This process doesn't do anything because it's gamma squared. So it normalizes the energy but doesn't do anything. Then there are other processes, second order also, where you tunnel in here and tunnel out there. This is this process. That's the leading one. Then you can there'll be higher order process, of course, but we are in a limit where the charging energy is large, tunneling is small. So this is the leakage. Yeah. Okay. Other questions? All right, so we already heard this morning about, just wanted to make some references to these papers about topological condo, and emphasize this sentence that the impurities, the spin we're talking about now is not, it's not an usual spin, but it's, I would call it a fractional spin, because it's a spin which is can only be addressed non-locally. If you want to talk to X of this one, we have to address these two. We want to talk to Z of this, we have to address these two. So it's been fractionalized, or whatever you want to call it. It's non-local, which is good because then it's protected. It's also more difficult to address it for the same reason. But that's a good thing, we think. All right, so this is the first example how to read out. So let's take this box and cut it off with two cutters here. So this is now in a Coulomb blockade, and we have a source and a drain. So now we can tunnel electrons from source to drain either through the bridge or through the island. So there will be interference between going here and going there, and so this is the total tunneling from source to drain. And as I said before, the phase of this one now depends on the state of gamma 2, gamma 4. And the conductance will then be the absolute square of the tunneling here. So it will read out, after we run current for a while, it will project the density matrix into an eigenstate of gamma 2, gamma 4, and we read out the state of the box. Because we have two different conduction values depending on expectation value of operator Z. So, but this was just reading out one, oops, I'm going the wrong direction, reading out, say, Z. How do we read out X or Y? For that, we have to make it more complicated, and we add another piece of wire here, which is a Majorana wire in Coulomb blockade regime with two Majoranas, so it's non-degenerate, but it serves as we can call it interference extender, because this is which was proposed by Fu, that you can have, he called it teleportation, we can call it something else. You tunnel in here and you tunnel out there, so they have a coherent transport over a distance which is long compared to, say, coherence length of the semiconductor. So that's why it's nice to use that one. Okay, so now, this coherence extender couples lead 1 to Majorana 3. So now we can go from 1 to 2, which will then go 3, 4. So 1 to 2, that's 3, 4, that's X. So that reads out the X operator. 1 to 3 goes boom, boom, in here, out there, so that reads Y, and the last one reads Z. So now we can read out all Pauli matrices with this device. But so this is, so we played with this for a while, and it maybe it's not the best because conduction measurement is not necessarily fast enough, and also it's hard to get all these wires in if you want to make more than one qubit. So an alternative was to use dots instead. So this is the same device as before, but instead of leads, there are 3 dots, dot 1, 2, and 3. And so one readout could be, you tune yourself into a regime where dot 1 is, let's see if I do it right, no, 2 and 3. Say 2 is occupied and 3 is empty, so the gates are like this. Then you tune them into resonance, so the electron which is here now wants to go here, or actually make Rabi oscillation between here and here. But the Rabi oscillation frequency will then depend on the state of the Majorana box, because it goes through here and picks up this minus sign depending on the sign of gamma 2 and gamma 4. So the splitting of the Rabi frequency splitting will depend on whether this is plus 1 or minus 1, so it's T0 plus T1 or T0 minus T1. And this difference in frequency can, in time domain, would look like this. You start, say, with dot 3 being empty, it starts oscillating, and then there will be different frequencies. So if you put yourself here, you have a good fidelity, which might not be the best way to do it, but at least in principle is the way to do it. How are we doing here? We're doing good. Another way would be to do the same readout, but in frequency domain, drive with input signal and then coupled to a resonator that couples onto this dot, and then see either in absorption or in phase change, read out the state of this one. So this is sort of a well-developed technique in other dot structures. A final way would be to not use two dots, but one dot, which is also, I think Stefan might be talking about this when talking about this paper here, with a large number of authors. So the way to think about this is that you have one dot coupled to two Majoranas. So the dot is D, Majoranas are 2 and 4. And so if it so happens that the argument of the phase of this one and the phase of this one is the same, then you can think of this as a real Majorana, and actually it doesn't split the degeneracy. But that's just one particular point, and if that happens, one would have to put a flux here and change it. But if they have different phases, then it would split the even-odd sectors to have different energies, and even-odd, I mean even-odd of this total system, the dot plus two Majoranas. So they will now have different energies as a function of detuning. And that allows a readout, because if we put ourselves, say, in the dot being full, for example, you start down here, and you pull up the gate so that you're here, and then measure the occupancy of the dot with the nearby charge detector. That will read out the parity of these two Majoranas, because these two curves are different. Because the coupling between dot and Majorana has different magnitudes depending on the parity of the Majoranas. Okay, so that was the three different readout procedures: conductance, dots, real time, or frequency, or one dot, or two dots. I mean, there's a number of ways, and I would say experiments would now have to figure out the best. But let's go on into Dreamland, and so this is a 2-qubit quantum computer. I will later go to a 4-qubit, where we could so have two copies of this box, you see, and we can use this, for example, for a belt test. One could initialize both qubits by running from 1 to 2, 1 to 2 from here to here, and 6 to 7 here to here. So that initializes us in an X eigenstate, these two boxes. And then a joint measurement, which would be running an electron from 4 to 5, or if it's just one dot, having them connected like that, which would make an interference between this path and this path. So it makes a joint measurement of these two, ZZ. So once we have done that, it's an entangled state, and we can go on and read out the different components and see if it behaves as a belt state should behave. Okay. So this measurement base seems to be a very natural thing to do in these kind of things, because we think we know how to measure, whereas doing usual gates, unitary operations, is not so obvious how to do. So let's try to see how far you can get with just measurement based. And if you look up in Prescott's notes, you can see how to make a C0 starting with 2 qubits, the C and the T, and then some ancilla qubit, and then do a series of measurements, which is first initialize the ancilla in an X eigenstate, well, actually a C eigenstate. I flipped it around, but okay. And then entangle it with the target, entangle it again with the control, and then do a readout, and maybe some more single Paulis. So we can do a C0 with an additional ancilla and then measurements. And in fact, one can. This is my 4-qubit quantum computer. You want to buy one? Yeah, drink on the beach. So it has two qubits, T and Z, like before control and target, and then two ancillas. And then we can run electrons from all of these dots and measure all these different combinations of either X in one or X in another one, or joint measurements between A1 and T, which is between these two here. So it's quite a number of dots, but this is how we have to make it if we want to make all these operations. And with that 4-qubit quantum computer, we can make a control knot, pi half rotation around Z and one around X, and therefore also a Hadamard. So that's the full Clifford algebra, Clifford gates you have by doing measurement based, which is still not universal. So maybe in the last few minutes, maybe also we will need to do single qubit operations, which we'll do by transferring electrons, in this case from 1 to 2. So put ourselves with this one occupied, change the gate, and spill it over to 2. And that performs a Pauli operator, because you put in one here and take it out there. And the good thing about this, it doesn't have to be adiabatic. You can do it any speed. From this, it looked like I would do it adiabatically, because I might end up here, which indeed I might, but it doesn't matter as long as we confirm that it was actually flipped. Because if we know it ended up here, then we know we have an odd number of this in perturbation theory, and we actually did it. So it doesn't sound so bad as it, because we can do it at any speed and then just wait for it to fall down. There's another possibility, which is to do the same kind of sweep from 2 to 3, but now put ourselves in a specific phase, which I mentioned before, so that these two Majoranas don't split, or so that the parity is not split. So that's one particular phase. If we do that particular phase and transfer an electron from here to there, we do an arbitrary phase rotation, which actually provides the last missing gate. Okay, I think I'm out of time. Okay, I'm sorry. Yeah. Okay, so what can go wrong? Many things, of course, can go wrong. We talked about quasiparticle poisoning. You can create particles that quasiparticles, one fall into one Majorana, another one goes somewhere else. That makes a Pauli error. You can think of all sorts of things. But one particular thing that one should also worry about is that when we do this tunneling, and this is now one dot and two Majoranas, we address the Majorana in a particular basis, we can say. If this gate fluctuates over time, the Majorana state will also change character. Because you can think of each instantaneous moment, we have to use Majorana in this. At this time is the Majorana at this time plus above gap states, if you want to think of in terms of expanding it. So therefore, if we wait of a certain number of time, parity might spill up virtually to the above gap states. And since we are not keeping track of the total parity, but only the parity of this low energy state, it might we lose information. I think that was not clear, but we can talk about it. So the way to calculate it is to couple the dot to the end of the superconductors, and then express this end state in terms of low energy states. And it turns out that one has to think of this Green's function. So this is the instantaneous Majoranas, and this is time evolution. So if time evolution is adiabatic, German is getting up adiabatically, everything is okay. If it's not adiabatic, it's not okay. So let me just flash the result of this consideration. I mean, maybe say this is related to an earlier paper by von Oppen and others, where Majorana was moving, and you see there's a certain speed at which you can move it. If you move it too fast, you know, there's a wind of quasiparticles being generated. And an estimate would be something like this, that there's a dephasing that has to do with the fluctuations of the gate voltage, which might not be so bad because this resistance is probably very small and so on. But there are things we need to think about. Okay. With that, I will put my summary off. Second order perturbation, yeah.